Okay, next talk title is Predictability-Based Curiosity-Guided Action Symbol Discovery. That presented by Burcu, Kilic. So when you're ready, please start.
Okay, so hi everyone. I'm Burcu from Boğaziçi University, and I will be presenting you our work, Predictability-Based Curiosity-Guided Action Symbol Discovery. So starting with our motivation, we know that humans and animals have the ability to perform symbolic or abstract reasoning about their environments. So in this work, we present a robotic agent that can learn symbolic representations of objects and actions, and explore out of curiosity without extrinsic rewards or extrinsic goals, and perform tree search to execute action sequences. So putting our motivation here, we'll go over them step by step. So firstly, I would like to show you where our work lies in the neuro-symbolic robotics literature by showing this taxonomy. So firstly, we fall in the category A because we don't have separate neural or symbolic engines, but we have them intertwined. And secondly, we are focusing on the emergence of symbols rather than giving them predefined. And we would like to be able to get the emergence of perceptual and action symbols simultaneously, and there aren't that many work being done in this category, and specifically we will focus on finding this emergence while we're optimizing for effect prediction. So next, we know that infants, animals, and humans benefit from intrinsic motivation and curiosity learning to more efficiently explore their environments. And in this literature, different curiosity signals have been suggested, like giving the effect prediction error to the action policy as a reward, or using learning progress for exploration, or choosing actions that would maximize the next state's entropy. And in our work, we will be focusing on something similar to the third one. We will be choosing actions that would maximize the effect prediction's entropy. So starting with our overview of the method. So we will have an effect predictor deep neural network that will take the continuous action parameters and object features to predict the object displacement or the effect. And through its latent space, we aim to be able to extract symbols, binary symbols. Next, to train this network, we will need some data of object, action, and effect. And we will get this data with a curiosity-based exploration module, which will use the entropy of this effect predictor network. Then we'll have a tree-based search planner, which will use the symbolic actions to reach a goal state. And then we propose an optimization method to be able to execute these symbolic actions by finding their corresponding continuous parameters. So starting with, again, an overview of our effect predictor neural network. So we have continuous action parameters. The robot always explores in a continuous environment, and we have continuous object features. We aim to encode them into embeddings, which later we will use step function to be able to binarize them. And we will train this network while we're predicting the effect. And the effect is the object displacement, or the final change in the object's position. So starting with more details on the network, starting with the action encoder. So I would like to first show what our continuous actions or parameterized actions are. So we define the continuous action as 3 points: start point, middle point, and the end point of the robot's trajectory. And at each point, we record the relative position to the object, the relative position of the end effector, and whether the gripper is open or closed. And again, with the object features are continuous as well. These are the dimensions or sizes of the objects and their types. And then we concatenate these embeddings, and through the decoder, we predict an effect distribution. So again, the effect is the change of the position in the object. Here we predict the distribution because we want to reflect the uncertainties in the environment and in the predicted effects better. And also on the symbol extraction part, by having tonnage activation function as the output function of the encoders, we guarantee that they're always between -1 and 1, so that we can use a binary step function to be able to binarize these embeddings. So now to train this model, we will need some data, and exploration data, which consists of actions, objects, and their effects. And we propose a method that can explore out of curiosity. So firstly, we sample candidate random actions, but we do not execute these on the robot because that will be too inefficient. We want to select efficient actions. So we pass all of these through our effect predictor neural network to find effect distributions for each of those actions. And then we select the one with the highest entropy, because highest entropy means highest uncertainty, and we would like to add the action to the train set which we are the most uncertain of. So now, up until now, we gathered the data and we trained our effect prediction model. Now, we would like to have some random continuous actions. And through the action encoder, we have encoded binary action symbols. But now, in this part, we have a symbolic goal action, and we would like to execute this symbolic action to see what it does on the object. So we need a mapping from this symbolic action to a continuous action parameter. And for this, we have sampled random continuous actions, and we propose an optimization method on these random continuous actions with the binary cross entropy loss between their encodings and our goal action symbol. And after some iterations of optimization, we take the mean of the continuous actions that give our goal action symbol, and we define it to be our corresponding continuous action parameters of our goal symbol. And next, now that we know the symbolic representations of our continuous actions, and we have also found a mapping from the symbolic domain to the continuous domain, now we can do tree search planning. So here we use a tree search based planning over this action primitives, symbolic action primitives that we have found, given an initial state to a goal state. So we have tested this planning on two different settings. First of them is the single object setting, in which the branch factor is the number of primitive actions. And we have also tested this over paired objects, where the setting has two objects in it. And in this one, the branch factor is 2 times the number of primitive actions. So now I would like to tell about our baselines. We will compare 3 different exploration modules. The first one is a random exploration, where the robot executes random actions to explore. And in the second one, the robot selects actions with large effects on the object to explore, because in random continuous action exploration, you get a lot of meaningless actions. And the third one is our method, the curiosity-based exploration module, as I said, where the robot selects actions with high entropy or high uncertainty in the effects. And as our experiment setup, we worked in Pybolot simulation with UR10 robot, and we used different objects, as you can see, with changing sizes from XYZ axis from 4 to 20 centimeters. And firstly, our model effect prediction errors. We did this test over a little bit more than 2,000 size test sets. And as you can see, our curiosity-based module performed better in predicting the effects. And I would also like to show some example learned primitives through our exploration module. Now you can see the pulling action, now the grasping action, pushing forward action, left pushing and right pushing. These are some example primitives. And now I can show an example plan, so maybe it's understood better. So in this single object example, we have an initial state and a goal state. And through our tree-based search, we would like to find the middle steps to how we can go to this goal state. And in this one, our planner solved it by pushing the plank left twice and then pulling it once. And a similar example in our paired object setting, and here we could also find the middle steps to get to a goal state. And I would also want to show our planning performance. So similar to these planning problems, we had a test set over 100 tests. And our model, CuriosityBased, that is trained with the CuriosityBased exploration module, found more diverse primitives, thus performed better in planning. So as our conclusions, so we are one of the first end-to-end deep learning model to find both object and action symbolic representations simultaneously. We also found that the curiosity-based exploration found more diverse primitives, so it also performed better in planning. And we have also demonstrated a tree-based search on action sequences. So as our future work, so firstly, we would like to examine how we can differentiate different effects during the executions, but have the same final outcome. Secondly, instead of a slow tree search planning, we would like to make this planning a full-scale, off-the-shelf symbolic planner like PDDL or probabilistic PDDL. And we tested this on the single object exploration, but it can also be tested in multi-object environments as well to be able to find relational affordance symbols or different skill symbols. So I will thank my lab, and thanks for listening to me.
Okay, thank you very much. So we can take about two questions. Do you have? Yeah, Pablo.
Hi, Burcu. I like the work, first of all. So, but I have the many things that I didn't get. Maybe in the paper is clear. So when do you encode the object, you encode the full image, or you encode the object itself? I didn't get that part. And also in the symbol representation, for me it was too fast how you transform it into some binary symbols, and that's why you are using the cross entropy, because if not, you could use any. If you have continuous representation of the object, for instance, you can use a KL. I don't know.
Yes. So. As the first question, we don't use the image of the object, but we use the object features, which are the sizes of the object and some type of the object, whether it's hollow or not. So we have features like that we use. And then for the second question, so as I can show here, so we find some latent embeddings that are produced by tonnage, and then we use this binary step function to be able to make them either zeros or ones. So we always have a 0, 1, 1 or 0, 0, 0 actions, action symbols.
Okay. Thanks.
Thanks for the question.
Okay, yeah. Answer question. Huh? Yeah, over there.
Hey. Thank you again. It was quite interesting. Again, I think I missed one step, which is when you talk about getting actions, choosing among like the random one, the one that have the higher variance, and you showed that you pass them through the encoder-decoder. But isn't that the encoder-decoder that you train with the actions? So how do you like connect the two?
Yes, thanks. So this is an active learning approach. Mm-hmm. So in each step before training, we do this operation. Then we train on the same network. So at each step, if the neural network has already learned about the action, then it would not choose it in another step. So this is an active learning setting. Thanks for the question.
Okay, thank you.
Thank you very much. So, sorry, time is up. So I want to move on to the next talk. Thank you very much.